Okay, so have a nice day, everyone. To you, sir, and to all my classmates right there. So, by the way, in this video, I'll be going to report our group report, and I am actually tasked with the equivalence of RAM computable and Turing machine computable functions, as well as the equivalence of the Turing machine and the recursive functions. But before that, I will also touch with the equivalence of RAM and the Turing machine before I'll go deep with the another functions. So, but before that one, let me also explain the RAM. What is it as is so that you will not begin to also forget that one. And when we say a RAM, just to give a idea, that is a computational models that mimic modern computer architecture, which also features an infinite array of memory cells, a program counter and registers, which is allowing constant time access to any memory locations regardless of position. So that means to say, as what you've learned in the previous discussion, that the RAM or the random access machine, there will be a infinite array of memory cells, which we can access that in any time, 0 to n. For example, we can mention that I want to access the location 20, so it will be a real time, and that is a best case time complexity if we will begin to um check the searching for that one. And that is a program counter to also track the instructions, and there will be a specific registers for a temporary storage for that one. So next, it is also a C let me click next, a CPU, which is an abstract um, computational model, which is designed to mimic the operations of the real world computers more closely than a Turing machine by allowing direct or random access to memory locations. So, as what I've mentioned, that we can access that one through mentioning or checking or searching a specific number, and it will be access on time or best case time complexity. So there will be a constant time accessibility for the RAM model. So in RAM model, there is here a specific steps that we follow. That is to read first and compute, as well as there will be write. So for reading that one, up to n processors simultaneously and stores the values in their local registers. So as what I mentioned, that for read, there will be a multiple processor, which is up to n, 0 to n, which our data, which read the data simultaneously and store in the local register. For example, we do have 0 to 2400, so something like that. So it will be registered in the local register, and for accessing that one, we can access through indexing. So for the compute, that is up to n processors perform basic arithmetic, logic, or logical operations on values in the register. So that means to say the processors can also perform basic arithmetic or a logical operations, which is being stored on the store data in the local registers that we store the values right there. So for write, that is up to n processors simultaneously write from their locations. That means to say that the processor write their results back to the designated location simultaneously. So I know that we've already learned about that, just only to touch the background, a quick background for that one. So let's actually proceed with the next which will be the Turing machine. So when we say Turing machine, as what we have learned last time, that is a function can be computed by a Turing machine and a computational model that reads and writes to an infinite tape to perform computation. So that is actually sequential, as what we have learned in the previous discussion, that we cannot access that in constant manner, um, which is different by the RAM model, because in RAM model we can specify the address and we can access that in constant time. However, here in the Turing machine, as what we have learned, that this is a Turing machine uses a infinite tape for reading and writing these symbols. So that means to say it can also perform the computations by following a set of rules. We learned the rules for that one already. And any functions that can be computed, such as the machine, which is referred to the Turing computable. So now let's move on to the equivalence of RAM computable and Turing machines computable function. So for that one, we have here a similarities and differences first, which they are both serves as abstract models and computations, and RAMs provide random access to memory, while the Turing machine requires sequential access, and the Turing machine use linear tape and for memory, and while RAM used an indexed space, access. So, so as we have known, and that one, that their similarities, both the Turing machine and random access machines can perform access, can access to a direct memory. However, while Turing machine require a sequential access. So if our memory access, if in our RAM, we can definitely access that in a time manner, which is best case. However, in our Turing machine, it could be average case or worst case time complexity. Now, for the memory structures for that one, the Turing machine, we are using the linear tape for memory, so which is sequential, where as the RAM, we are using the index memory for faster access. So let's actually move on with the equivalence for that one. So the equivalence, let me click next. So the equivalence, RAM and the Turing machine are computationally equivalent, meaning they can both compute the same functions. So they can actually simulate each other with at most polynomial overhead in time and constant factor overhead in space. So that means to say, by our the Turing machine and RAM and Turing machine are computationally equivalent, so they can compute vice versa. They can simulate vice versa. It could be RAM simulation by Turing machine, or Turing machine um, based or using or simulating the RAM model. So we can actually check that out later on how we can organize or use those platform by simulation, those RAM by TM and TM by RAM. So we'll be going to try to see that later on. So for here then, as the next one here, simulation of the Turing machine, we do have here simulation of Turing machine by RAM, which representing the Turing machine tape as array in RAM's memory. And we are also implementing transition function using RAM instructions. And we also have to track tape head position using a register. So here then, we are just following that steps, particular we are also observing, since as we've mentioned earlier, that we do have a differences between the two. However, right now, by simulating the Turing machine by RAM, it is representing the representing the Turing machine's tape as array in our RAM's memory. So it means that means to say represent the Turing machine's tape as an array in our RAM memory. And for implementing the transitions function, we are using RAM instruction to implement the Turing machine transition function. And we also tracking the tape head position with a RAM register. And we can point that out later on. How does it work? So um, let's go ahead. How can we simulate the Turing machine using the RAM model? Okay, so let's continue with that one with the simulations already. So the Turing machines by RAM, we have the components here, which is first the tape. So for the tape, we can simulate an infinite tape of a Turing machine using an array in the RAM model. And we are using two arrays for arrays, which is the right side and the left side of the tape. So left side, if our we are representing this one if our Turing machine moves to the left and pass the left pass, then with the initial position, and that also handle the negative index by mapping them to that array. And for our head position, we also do have here um, using variable head to track the current position of the Turing machine's tape head. And we also do have the state, which we store the Turing machine's current state in variable state. So in that situation, anyway, for that one, we are trying to what we call this one represent as what I mentioned earlier, the Turing machine tape as an array in our RAM's memory. That's the first component. And we also use the RAM instruction to execute the Turing machine's transition function. And afterwards, we are tracking to the tape has position with registers. That is the thing that we have to also do here. So let's actually move on. By the way, with the second, we also have here encoding a transition function. So which is we have here the transition function symbol, which Q and A, and we have the what we call this one Q and AD as a lookup table conditional statements in the RAM model. I forgot what is that one. What they will be with the. So let's try to define this one here. So there is a for this. This is representing the new state, and this one for the A. I forgot what does it. How can we call that one? So that is a symbol to right, symbol to right, and the D direction to move left. It could be left and right. Then okay, so for the Q with hyphen, like I said, that will be the new state, and with the A with hyphen symbol to right. So the same thing with the Q, that is the current state, and the A with the current symbol under the tape head, and the D, that is the direction where we will proceed. Then it could be a direction to our tape head. It could be in our left side, or it could be in our right side. So that is the representations for that one. Next will be we are simulating the TM transition. We have here the red, the current symbol under the tape head. And after that one, we are using transition table to determine the new state symbol to right and head movement direction. So, and we also update the tape, which we first write the symbol for the current position. And that is equals to head, for example, then plus equals to 1 for right, and head minus equals to 1 for left state. So that means to say in simulation for Turing machine transition on a RAM model, we are reading first the current symbol under the tape head. And after that, we use the transition table to determine those tuples that we do have, the new state, which will be the Q with hyphen and the symbol which symbol to write? Is it A with the hyphen and the represent the A with the hyphen and the head movement, the direction that we've mentioned, and afterwards we update that we write the new symbol to the current tape position after we move the head. It could be +1 or it could be -1 for left. That is how it works here in Turing machine representing by the RAM model. So let's try to work on with that later on. So for the 4, we also handling the infinite tape. Dynamically allocate memory as needed in the RAM model, and we also extend the tape arrays moves beyond their current bounds. And afterwards, we also perform the halting condition, which the RAM program should halt if the Turing machine reaches a halting stage. And for this one, by the way, for handling the infinite tape, we are dynamically allocating memory in the RAM to extend the tape when it moves to the current bounds. And after that, the RAM programs halts when the Turing machine reaches a halting state. So when we say halting, that's the indication that we are that we stop already. So first, then here, let's have it. Suppose we have a Turing machines that perform a unary addition on input um, x plus y, where our x and y are represented as a sequence of 1, which is separated by a single zeros. So say, for example, your x represented as 3 ones and y is equals to 1. So it must be our input, it must be in 1, 1, 1, 1, and 0, 1. So let me correct that moment. So that's great. So it will be input 111 011 supposedly. So we will follow the algorithm, the states, which our states includes the Q. Those are, for example, we are using Q0, then Q1, and then and so on. Those includes then the QH, which is our halting stage. So let me erase that so that we can figure it out. Really, so sorry. So by the way, the symbol for this one, this will be our state, the same thing. The Q0 down to the Q K, so on and so forth. And then this transition function that includes, for the transition function, we are following the Q, then by our input, and then so on and so forth. The same thing by input and the direction by, it could be the direction, it could be -1 for left and +1 for the right. So that's how we work on with that one. So we first then initialize the diba? We have to load the Turing machine's initial state. So that will be set as Q0. So for that one, let me fix it in here. Okay. So for this one, by initializing, we load the Turing machine's initial state to the Q0. So suppose that this will be our Q0. And in our Q0, we have to load the tape's input symbol into the array. So we also loop until halting state. We fetch the state or symbol from the tape and transition table until the we write the new symbol afterwards we write the new symbol to the tape. So let's try to check it in here. This must be look like that. For example, we have here the Q0. We set that into we follow the algorithm that we've identified earlier for the unary addition. Suppose we have that performing the unary problem, this one. So our graph represented by the Turing machine by Ram example will be represented as like this. So our states here then will be the Q0, which is our initial state, and our Q1, Q2, and QH is our inputs. So our QH right there is our halting state, and our Q2, that is our separator, and the Q1 as well. So here, let me discuss that one. Why is it like this? So since our X is 1 and your Y is 1, 1, and it must be 1, 1, 1, 0, 1, 1, and then we are doing the unary, which is adding the X plus 1 at it, and it must be 5, diba? So for this one here, our what we call this one, transition, we are following, since as what I mentioned earlier, we initialize, then we loop until the halting state. So we are doing here, we'll loop the functions. Let's try to check that one by one. We're doing the loops for that. So since 1, 1, 1 is what we've mentioned, so we can loop 1 at the, let me see. So we can loop the 1. So this one here. So we loop 1, and the input will be, so this will be the representation for that one. Let me check it. So yes, this is your really sorry, I'm not certain with that. Yes, that's correct. This is your direction. So your Q0, since this is represented by your X, so your Q0 will loop the 1, since we can check, we can 1, 1, 1, 1, or so on and so forth. And that is here. Okay, Q0, that is separated here. So, second. Okay, so for our functions here then, for their Q0, that means to say that we are moving right over once. So for that instance, our current state is actually placed in Q0, diba? So what does it mean is, in your current state for the Q, that is Q0, and your current symbol for that one, since we are looping the X, so that is 1. Then the new state for our direction here will be Q0, and our next symbol or the new input will be 1. So that is we write 1 or no change of the symbol. So we write 1 in our tape, and then the movement will be right. So that's the Turing machine remains in our state Q0 and keeps reading 1 under the tape head, which is we are moving to the right position. So that means to say we plus 1. So that is how it worked for this transition for the Q0. And afterwards, for our Q0 0 input, which is here, we are our current state Q0, and our current symbol will be 0. So our Q0, that is our separator. We stop at separator 0. So this will be our separator. And then our new state will be in our Q1. So that is directed into Q1. And you are writing 0. So we stop by 0. And we are plus, we increment, or we plus 1. That is, we are doing the right movement, or the distance is right. So in the right position. So now, afterwards, we also do have the transition for Q1. From Q1, we have the input of Y, which is the 1. The same thing. So we loop the 1 since the and this one, by the way, in our 00R, in the transition of that one, the Turing machines transition to the state Q1, to that points to the Q1, diba? And we write the 0 and under Q0 under our tape head. So our tape head is pointing now into, so say for example, here this will be our tape head. So earlier we inputted in our tape head once, diba? So 0, say for example, so that points to the right position. Now we plus 1, and this is our address right now for that transition. So it then moves to right. Afterwards, after moving to right, this will be our new transition, which is Q1, and our current state for the Q1 with a current with the current symbol of 1. So this is our current symbol. And after that one, we write in our Q1 1, which is moving, or the distance is right. So in state Q1, that means to say our Turing machine, we are continuing to read the 1 input. Afterwards, here, that is actually under our tape head. So our tape head, we plus 1, we increment 1, and moves by moving, incrementing, that is plus 1, since we are not decrementing to 1. So now in your tape head, you do that. We move right to find the end, and after that one, we also do append. So by the way, in your head for in your tape, you've actually inputted right there as like that. 1 0 1 1 0, then 1 1. So there will be a space, something like that, since that is the representation of our what we call this one, in our tape, that we do have the blank spaces. Now, afterwards, we have here the fourth transition, which is our Q1 with a empty input. So that is for empty input, that is pointing to Q2. So we are pointing to Q2. So when the Turing machines encounter a blank space already, it transitions to state Q2. So we transition to the state Q2, then we are writing the input 1. And after that, we are writing the input 1 into the blank spaces in our tape. So that means to say right now, 1 1 1 0 1 1, since that is separated by 0. So our goal is to plus, diba? So 1 1 1, and then writes 1 on the blank space and move that into left. So we move into left. So that means to say we append 1 and start moving back. So we move back here. So means to say we move back until we repeat that 1, until we can append 1 into the right position. So we move left, then we append 1 into the right side. We move left, we append 1 into the right side, and we move until such time the functions will be complete. So that's actually how does it work. So afterwards, for the fifth transition, we have the Q2. We are in the Q2, which we also do have the input. When the Turing machine reads 1 under the tape head, so when we are reading here, then in our tape head already, say for example, this one, and under the tape head, we continues moving left. So as what I mentioned earlier, we continues move left, and then we append the 1 into the right side as well. And we continues moving left and we append 1. We write 1 in our tape head and we move left. That's how it works. So we move left. After that one, when our current state is in Q2 and our current symbol will be 0, and that one, by the way, excuse me, the Turing machine transitions back to the state Q0. When it encounters 0, we write 0 on our on that position and move right. So say for example here then, from our left earlier, we move left, and when we encounter 0 here, so we stop right there. We moves right. So we can move right, which is repeat 1 and so on. So after that, since we input 0 in our we write 0 in our tape head. So say for example, so we are done visiting 111 111, so that is already 5. We perform the x plus y, so that is total of 5 already then. So right now, if everything was done, the Turing machines reaches a blank the blank spaces already on state Q0. If we are in a state Q0, it holds or it stops in QH. So it holds in state QH and then stopping further processing. So we don't have we are not writing anymore in our empty spaces. So therefore our functions or our x plus y unary, the unary of x plus y, which will be the input of 111. When we perform the searching or reading that one earlier by performing the distance left and right, so we perform by adding that here, that it is equals to 5. So that is how it does it work for Turing machine by RAM simulation. So we will move on to the next one as well by the RAM by Turing machine. So let's take it one by one. For the RAM computable by performing the Turing machines as well. So by the way, for the RAM by Turing machine, the simulation of RAM by Turing machine, we first encode the RAM memory and register that on a Turing machine's tape. So that means to say, we represent the RAM's memory and registers on the Turing machine's tape. So each cell on the tape can correspond to a memory location or a register value, and we use the tape to store the data and the instructions as needed. And after that, we implement the RAM instruction using the Turing machine's transition. That means to say that we are translating the RAM instructions into the Turing machine's transitions, and each transition we corresponds that to a specific RAM instruction. Example, we do have earlier the read, write, compute, and then we alters the state or contents of the tape accordingly. And that allows us the Turing machines to perform the same operation as a RAM model, but in a sequential manner. So after whereas we use multiple tapes to efficiently manage different aspects of RAM simulation, which includes the program, the memory, and the register. So we are utilizing the multiple tapes here on the Turing machine to separate, efficiently manage, and the different aspect of the RAM simulation. So for the program tape, that which is the responsible for holding the instruction, and the memory tape that is responsible for storing data values, and the register tape, which is managing the register values. So this is actually organizing or helping to maintain the clarity and efficiency in simulation, the different parts of a RAM using a Turing machine. So afterwards, we have here, they consist of, as what I mentioned, register, instruction, and theirs, and so on. So first, register. I used to store values in RAM accessing a register, which we have the memory location, which takes a constant time. So the purpose of our register, that we use to store values in RAM, and by accessing the register in our memory location, it will be a constant time. That also ensures a quick retrieval and searching and storage of data as well. So next will be the instructions, which will be the RAM typically performs operations such as the loading, storing, arithmetic operation, branching, and so on. So for that one, for loading, we transfer the data from the memory to a register. And for storing na naman, we are transferring the data from a register to the memory. Then arithmetic operations, those are the addition, subtraction, and so on, and branching. We redirect the program flow based on conditions such as jumping statement, conditional branches, and so on. So we have here the same problem as we have earlier. We simulate a RAM program that we are adding two numbers, X and Y, and store the results in another location, Z. So we first perform, in our first block, we load X, we load the value from memory location, 1 into register, 1, and we add Y, add value from memory location 2 to register 1. To say, for example, this will be the X, and that will be 1, 1, 1. And we load Y into our register, which is 1, 1 as well. And we have Z, which we can store there, our output. So we store the result in memory location 3. So our location 1, for example, that will be our store for 1 X and store for Y, and we perform the addition and we store that into our Z location. So let's go ahead and check it in here. So we have here the representation. So say, for example, you have right now the Q0 as the start, the tape head points there, for example. So we mark as start as part of 1, and that inputs to 1 and move to the right position. So mark as part of 1 in terms of our X. So since that is equals to 1, 1, 1, and so since your Y is equals to 1, 1, and our input will be 1, 1, 1, then 0, 1, 1, 1, and that must be equals to X plus Y since we are adding. So for our start position, when we input our X, so this will be 1, 1, 1, and that goes to right. So that will be that will go to our Q1, which we have, if our tape head will points right there, that is the separator. The head moves to the separator, which is our 0. And we continue to the second block contains the Y, and the Y will be the another in another block. And then so after we move to the separator, which will be the 0, so our separator, our input right there will be 0, and that moves to the right position, and that moves to the Q2. We perform there the addition. So in our by performing that one in Q2, we perform addition by moving to the second memory block, which is here then, and making 1 in Y, which is this one, and um and then we add the value in our X as well. So moving to state Q3, we store the value, we store the result. So after performing the addition in our Q2, we return to state Q3. That's why we put here 1. Our input will be X and goes to the right position. So we are using X in Turing machine since that signifies also that we cannot that the item has been processed or already visited. So when a Turing machine is already simulating an addition or operation or searching operation, a symbol marks any specific indication as it is already being counted or being used or visited. So after that, we store our value in our Q3, which we print the results right there will be 111 plus 11. That will be 5 here. So we store the result. After performing the addition, we store the results right here, and we return to state QF afterwards, since we will hold to the final state. So we stop in our final state after calculating that one. So um we stop right there after it has been accepted. So that's how it worked for Turing machine by simulating the RAM model. And then let's continue to the equivalence of Turing machines, Turing computable functions, and partial recursive functions. But before that, let's try to define first what will be a recursive function. So the partial recursive function, that is a type of computable function which is defined over natural number that may not produce an output for every input. So the property of every input, every of partial recursive function may be undefined for some inputs, which implies that the computation might not hold. And then it corresponds that to a computation by a Turing machine that holds and outputs a result for inputs where the function is defined and loops indefinitely for input where it is undefined. So in recursive function, it is also talking the class of function that can be defined using a set of functions, compositions, primitive recursion, and minimizations operations. So they provide a mathematical model of computation, which is equivalent to the power of a Turing machine. And that is defined as a set. There will be a base case for that, and there will be a recursive case for that one. And after the let's continue. The equivalence of Turing machine and recursive function is a fundamental result in computability theory, and that established that these two seemingly different models of computations, which also have the same expressive power and can compute the same class of function, and the Church-Turing thesis, which states that any effectively calculable function can be computed by a Turing machine or expressed as a recursive function, is supported by this equivalence. So the equivalence of Turing machine and recursive function is a fundamental result of computability theory, is what being mentioned right there. And we establish a model that compute the same expressive power, and we are computing the same class of functions as well. So by that, let's try to see here. Every Turing computable function is a partial recursive function, or any functions computed by a Turing machine can be expressed in terms of primitive recursion and minimization. So every partial recursive function is Turing computable, or any function defined using primitive recursion and minimization can be implemented by a Turing machine. So let's try to check there as well. How does it work? Let's try to understand the this matters. How does Turing machine by partial recursive functions work as well? So let's try to take it one by one. Okay, so we will move on to the Turing machine by partial recursive function simulation. So for that, we are having here Turing machines can simulate partial recursive function. So the Turing machine can perform basic arithmetic operation, the successor, addition, multiplication, and so on. And it can also handle recursive definition by simulating the step-by-step evaluations of a function. And we also do have the recursion minimization that involves searching for a value that satisfies a condition and that can be implemented by a Turing machine using iteration, iterative commutation, and halting when the condition is already met. So we have here the example partial recursive definition of addition, which will be the same thing, which we have defined f of x and y, which is x plus 1, where our base case is when f is equals to 0, that is equals to x, and if your f of x, y plus 1, that is defined as f of x and y plus 1 is our inductive cases or the recursive case. And our problem statement we compute the f of x and y, which is equals to x plus y. So our unary case earlier, which is x is equals to 3 and y is equals to 2, which is represented by 1, 1, 1, 0, 1, 1. So the tape layout must be like this. Actually, since we have the tape layout for the Turing machines, as what we've mentioned, we encountered that Turing machines represented by a tape as well. So steps right now is have the states Q0, Q1, Q2, and QH, and we'll be going to see the graph later on. And x is equal to 3 and y is equal to 2, and our initial tape will be that one. So our goal for as what we have, our initial tape is 1100 011, then spaces. So for that one, our current state, suppose that we are in the Q0. So our current symbol for that will be 1. And our input will be 1, and we are directing to the right position. So that means to say that the machine moves right over the first block of 1, and the head moves to the 0 separator. So our head moves to the 0 operators afterwards after we move to the right position. So 1, then we will move to the right position, which we are pointing directly to 0 already, and we skip the operator. So we are having the 0, Q0, and our current symbol for that one will be 0, and we are pointing to the right. We are having the direction of right. So here, Q0, Q1, R, that's here, right position, and here, Q0, your symbol, current symbol will be 0, and you will point to Q1, and your input will be 0. We write here we visit the 0, and we move to the right position, and your machine right now moves to the state of Q1, and then moves to the first one in Y. So we move in one Y. So this one we move here then. So that's why we have we moves right to the first, and our head moves to the one of Y. So we are moving here already in that position. Afterwards, we move to end Y. So we move to end Y. So this one here, we have the transition of Q1 to 1, and our input will be 1, and we move to right position. So our machine moves right over to the 1, which is in Y, and then your head moves to the blank spaces after you move your 1, then you move here into your blank spaces after Y. So after that one, since we visited, we moved our we moved to the right position, and our input is 1. So after that, you are in the Q1 already. So you visited the 1 in your tape, your head is already in the last, and you move into the empty spaces. So you have to append 1 here in your empty spaces. So we have Q1, and our input will be empty, and you have to append 1 to the left side. So in our left side, you have to append that into the empty spaces. So since we are doing x plus y later on, so we check your our machine writes 1 at the blank space, then we transition to Q2. So here then we transition to Q2 and we move left. So we move left and we print out that into our tape empty spaces, and our head moves back to the last one in our Y. So is to say it will become 1 1 1 right now, and then afterwards we move left to the separator. So here the Q2, we are already in the Q2 and our input will be 1, for example. So our machine moves left over to 1. So the 1 is in Y. So 1 is in Y. We move in our next position, we append 1. So the head moves to the 0 operator. We will incrementally move to left. So until we append, and it will become 5 afterwards. So Q2, we are in the Q2 position right now, and we will our input will be 0 and your input as well will be 0, since after you visited everything, after you append that here, you will be visited 0 and it will be stored into the empty spaces, and it will return to the first block of X and will return to the 0, Q0. That's why we have here, we return to the Q first block, and after that one, our machine transition to Q0 and moves right to the first one in X. So we move right to the first one in X and we do it in a cycle, and the head moves to the one in X afterwards. Since everything was already visited, the machine repeats steps 1 to 6, consuming 1 from X and appending 1 to Y, and conform the 5 during each cycle. Ga-append tayo 1, di ba? Afterwards, we come we when we are doing everything, the operation, we can achieve the final state, which will be in the QH. So when all 1 is in X already, when all 1 in X are consumed and that is already printed or appended into the empty spaces, so where it will become, our machine will transition to the halting state, and that is the QH, and stop everything. So that's why we have S right there. So our tape conform 5 as we simulate the Turing machine by partial recursive, since we did that in an incremental step-by-step procedure, and the Turing machine successfully simulated the addition. So 3 plus 2, earlier 2 plus 3, so that is consuming X from, we are consuming ones from X, and we are appending ones from X to append to Y into the empty spaces, and we halt when X is fully consumed. So we halt and we stop everything, and we conform already the step by step, and we achieve the 5 stages. So the recursive definition translates into a computational process where starting with X and Y, and we increment X by 1 and Y times, and afterwards we form a cycle, and after we finish everything, we halt that, and that's the stop of our steps. So afterwards, let's try to check also how does it work for the partial recursive function by Turing machine. So partial recursive function can simulate Turing machines, and the configuration of Turing machines using state, tape, contents, and head position can be encoded as natural numbers. And then transition function of the Turing machine can be simulated by using primitive and minimization, effectively reproducing the machine's computation. So let's try to check that there. The functions include base case, which is having the initial value, and recursive case defined in terms of the function, and uncomputable cases possibly undefined for some input. So a Turing machine can simulate this function because it provides a concrete way to compute them in a step-by-step manner. Since in computing recursion function, there will be a recursion step or recursive cases, and then it will stop up until we found the base case already. So suppose that we have here an example for the factorial function of f of n, which is n factorial. So our base case for that one, f of 0 will be equals to 1. So our goal is f of n plus 1 is equals to n plus 1 times to the factorial of n. So which is our recursive cases or inductive case. So a Turing machine components for factorial function, tape, we have the representation, the tape representation, the states, and transition. So let's try to figure out. The tape transition, we have the input, n is encoded in unary as 111, and for n times, and the output of f of n in unary. So the states and transition, we read n, then we move to process multiplication, and we initialize the accumulator with 1. Factorial starts as 1, then multiply the current factorial value by the next number, and then halt will with the results. So let's try to figure it out. So our goal is f of 3, which is equals to 6. So in that procedure, we will follow these steps. So we are following that manner, by the way. So initial tape, the input tape, the unary encoding of n is equals to 3. So is represented as 1, 1. Then that is in our tape, for example. So the blank spaces on the tape, that is where we insert later on. And then our initialization step will be in the Q0. Say, for example, we are in the Q0 right now. So in your Q0, the Turing machine starts in state Q0. So our goal is to move right. Our goal is to move right. So here, Q01, then your input Q0 still 1, and that is right. So that is how it is represented. Now, afterwards, let's try to check here. Okay, that's the final steps. So we will check that later on. Now, the same thing, procedure. So for that one, we represented the Q0 as 1. So that will be your X. Here, 111, that is set by 3. So that is already in your tape. So we transition to Q1 after processing the N. So we process already your N, the 1. Afterwards, we transition from 0, we transition the blank symbol, spaces. So Q0, that we have the blank, and we also have input blank, and we move left. So we move left. So that means to say we move left. 1 second. So since we already identified the n is equals to 3 here, so that is already added into your tape. So we move to the next position, the Q1. We transition to Q1 when a blank space is found. So we move over 111 and stop at blank spaces. Then we transition that to Q1. And then our head position will be in your 1. So since after Q1, we will do this is our separation actually, and after we will do the multiplication steps. So in our multiplication step in Q2, you are doing here from Q1, you have the input 1, and that one, you write 1 into the right position. So we write in we write 1 in your next position into your empty spaces, and then the Turing machine multiplies the current factorial value. So you visit the first one, then you times that. So the Turing machine multiplies the current factorial value by the next number working iteration. So we have this step, we copy current factorial value. So we visit 1 and we copy current value of f of n, starting with 1 into a new block of empty spaces right there. So our we proceed afterwards, since that is already we will multiply that. So we visited 1 and we will append that into the empty spaces, since we will duplicate that by itself. So from Q2, our input 1 and we write 1 and we continue the steps. So the execution right there, we append a new one, since right there earlier in your Q1 we move to the Q1. We move to the Q1, which is you're performing into the right position. So that will be 1R. So in your Q2, once you are in Q2, you append a new one into this into the head into the tape, into the empty tape, and while you are performing one right position, and for each one in the current. So from each one you proceed one earlier, then this one will be duplicated and inserted into the empty spaces. So we copy 3 is from the input block 111, so we will copy that and insert that there. So on. We do the recursion step, we do the recursive manner. So for example, you visit this one, you duplicated, you visit and you duplicated. That's how it works. So you certainly do that in a step-by-step manner. Afterwards, you will return to start of the n is equals to 3. We block the next iteration. After that, you are already in Q2, for example. So the final step right there, we move left over. So after we append everything, so we have the Q2 procedure. Here we will store the result after in QH. So after the Turing machine finish all iteration, when S is already exhausted, so it will halt and print the result in your final state. So that's why Q2 and your QH that will print your variables. So that will be 6 already, and that is the final state. The tape after halts, by the way, will become 111, 111, since while doing this one here, we visit, then we store, and we append. So we visit, we store, we visit, we store. So it will, after we certainly do everything in a execution manner, we move back into the left, diba, earlier, and we move to the right, then we append to the right. So it will produce a 6 number by duplicating this one, appending that into the right most manner into your tape. So therefore, we achieve with your factorial of 3, that is 6. So that is the representation of this one, or the transition rules for f of n. Your goal for f of 3, that is equals to 6. Since you are visiting this one, then you append into the empty spaces. While you visit, you append, visit, append. While you do that recursively, afterwards, if that already being found, it will be halted and you will print the result, and that's the final procedure. So that's how it worked for the partial recursive simulation using the Turing machine. So hopefully that it's clear. I do hope that's correct. If ever that there will be some corrections for that, please let me know, sir. Thank you so much and goodbye, classmates.